Hey guys, um, this kind of review video, I just wanted to give you kind of like a refresher, well, just an example about direct sums. Okay, because I think this topic I did not too much put too much stuff in the practice question, so I wanted to make sure to not leave it out. Okay, so let's do just like kind of a toy problem or something. So let v equals r2, just keep things simple, I guess. And u is just going to be all the vectors in R2 whose first and second coordinates are equal. It's a subspace of V. And what's the question? So far I haven't written down a question, so the question is find W such that A plus W equals R2. Let's call this part A. And then part B, define T from R2 to R2 by the rule that T of xy is just going to be 2y and then second coordinate x plus y. Okay, and we'll show that T of u contained in u and and then yeah, okay, and then the second question is like for W from part A, look at T from W to R2 and decompose this. T of W equals call it T1 of u plus T2, or sorry, T1 of W. I'll call it Tu of W plus Tw of W here. Tu is going to go from W to U and Tw is going to go from W to W. Okay. The reasoning being that R2 is a direct sum of U plus W, so T of W is going to be in R2, so T of W is going to be a sum of something in U plus something in W uniquely. Let's just like find out formulas for these two things, depending on what W is. Okay. So hopefully that's enough to kind of get into things. Okay, so first let's do part A. So part A says, let me just remind, so solution, part A, again, U is a subspace of the things where the first and second coordinates are the same, unless we need to find W such that W plus U equals R2. Okay, and what are some like properties of W? Well, U has dimension 1. A basis for U is just like there's many bases, but one basis might be 1, 1. Okay. So since the dimension of U is 1, the dimension of R2 is 2, so the dimension of W must also be 1. So a basis for W has one element. Okay, so a basis for U is 1, 1. So what we're looking for is a basis. We'll look for a basis for W. Well, a basis for W is just one vector. So we're just looking for a vector for W such that W with 1, 1 is linearly independent. Right? That's one way to do it anyways. Because if these two vectors are linearly independent, well, the span of 1, 1 and the span of W will have 0 intersection, and their sum will have dimension 2, so it'll be all of R2. So you can check that the conditions are satisfied for a direct sum. Okay. And how do we look for a W that's linearly independent from 1, 1? I'll just take any W that's not a multiple of 1, 1. And, okay. So, suppose W is not equal to CC, where C runs over all scalars. In other words, suppose that the first and second coordinate of W are different. Okay. So W, which is going to be like W1, W2, and W1 is not equal to W2. Okay. So now let W be the span of W and it follows that U plus W equals R2. So why? Well, because you know, you can either say that if you combine the basis for U with the basis of W, you get a basis of R2, or you can just kind of argue directly, you know, because if anything that is a scalar multiple of W will have different first and second coordinates, unless it's just the multiple 0, unless it's the 0 vector, and anything that's in U has equal first and second coordinates. So the only thing that they have in common is a 0 vector. Okay, because if, let's say, U is in U intersect W, and U equals U1, U2, then U1 equals U2, but if U is in W, then U1 is not equal to U2, unless you're in the specific case when they're both 0. Okay. So U1 equals U2 equals 0. Okay. So U intersect W equals 0. And what about U plus W? Well, U plus W has dimension 2, and U plus W is contained in R2, and that has dimension 2 as well. So that tells you that U plus W actually equals R2. Okay. So we found a bunch of subspaces W, where you get W, where R2 is the direct sum of W and U. We can kind of draw a picture of them too. So actually this line, this is U, and then take any line with where like any line going through a vector which isn't on U, and that can be W. So W can be W can be any line intersecting the origin, but that's not the same as U. Okay, that'll work. Okay. So you want to think about it. One way to look at it is you can choose W to pass through any point on this like half circle, not including these two endpoints. Okay. If you want to think about it like that. Okay. That's one way to think about it. Yep. Okay. Now let us look at right, so the key point is that for R2, we want to write R2 as a direct sum of U and something. We just need to choose the and something to we just need to choose it to not intersect U except for the 0 vector. Okay. Okay. Well, let's do part B. Okay, so part B. So U again is like this, XX, where X is real. And W is going to be like C times W1, W2, where C is a real number. Where W1 is not equal to W2, and W is fixed for this question. but unknown, you know. Okay, and then what is t? T is this linear transformation given by 2y and x plus y. Okay, so let's show t of u is a subset of u. Well, t of xx. The definition of t of xy says 2 times second coordinate in the first coordinate. So second coordinate is x, and then add the 2 coordinates for the second coordinate. So you get x plus x, which is 2x. Okay, well that's just 2 times xx, and that's in u. Okay, so t of any vector in u is also in u. So t of u is contained in u. Okay. Now let's find decomposition. Xy equals maybe like a times 1, 1 plus b times w1, w2. Okay. Okay, let's try and find it. Well, we just we just row reduce. This minus this. This minus this. Okay. Now remember, all we know about W1 and W2 is that they're not equal. Well, they're not equal, so we can just divide by W2 minus W1. Okay, and then we'll subtract. So x minus W1 times this. Okay, and let's simplify. So let's just simplify this term. Well, we get all over W2 minus W1. You get x W2 minus W1 minus W2 y minus x. And we get x W2 W2 so we get plus 2xW2 minus xW1 minus W2y or W2 minus W1. Something like that anyways. Okay. So it tells me that the first coordinate is this thing and the second coordinate is this. Okay. So to make things simpler, um, because we can fix our basis, so we can choose our favorite basis of W. Okay, so let's try and choose a basis of W. So here's the basis we started with. Let's just try and multiply it so that C times W1 or C times W2 minus C times W1. Let's try and normalize, like this minus this becomes 1. Okay. Well, if you do that, you can do that by just choosing C to be 1 over W2 minus W1. Okay. So let our basis for W be this vector W. And this will just be, I don't want to use W again, so I'll just call it, I guess A1, A2. So now, A2 minus A1 equals W2 over minus W1 over W2 minus W1 equals 1. And in our original formula, so now if we solve xy equals a times 1, 1 plus b times a1, a2, then we get the solution that a equals x minus a2 times y minus x, and b equals y minus x. We simplify this further, we get, you get 1 plus a2 x minus a2 y. Okay. So now let's figure out what is T of A1, A2. Well, T of A1, A2, the definition of T just says 2 times the second coordinate and then add the 2 coordinates. Okay, and we want to write this as something times 1, 1 plus something times A1, A2. Okay, but we've already shown how to find the somethings. The first coordinate is going to be 1 plus A2 times the x coordinate, which is 2A2. And then minus A2, there's a y coordinate, A1 plus A2. And that's times 1, 1, plus, and then plus y minus x. So that is this minus this, which is A1 minus A2 times A1, A2. So, and A2 minus A1 is 1, so A1 minus A2 is negative 1. So now the last part is just to kind of okay. So now we have our linear transformation from W to R2 satisfies T of CA1, CA2. That's going to be 1 plus A2, 2CA2 minus A2, CA1 plus A2, 1 plus A1 minus A2 times C times A1, A2. Okay, so we want to write this as something going from W to U and something going from W to W. Where TU goes from W to U, TW goes from W to W. Sorry. Okay. Okay, and then TU should kind of be like this. So TU of CA1, CA2, that should be I need this a lot of room for it, but both coordinates. So if I multiply everything out, I get 2CA2, and then I get so I get a 2CA2 then I get 2CA2 squared, and then minus CA2 squared, so I get plus CA2 squared, and then I get minus CA2A1. Okay. And then in the second coordinate I get the same thing. Okay. So notice this is, so these are all the vectors in W, and this is a vector in U since its two coordinates are the same. Now TW is defined by, well, it takes a vector in W. Vectors in W's are just multiple of A1, A2. And you just do, if we write it out, it's just CA1, A1 minus A2, and then CA2, A1 minus A2. Oh yeah, now let's remember A1 minus A2 is -1. That's even better. TW is just, this is -1, this is -1. So TW is just multiplication by -1. Okay. And that kind of finishes off the question that I asked, but now we can also ask, what is the matrix of T? Well, our basis relative to our basis 1, 1, and then A1, A2. Well, we've seen that T of 1, 1 is just 2, 1, 1. So that means the first column is just 2, 0. And T of A1, A2, we've already worked it out. It's just, well, it's just -1 times A1, A2. And then like something complicated here, which is, 2A2 plus A2 squared, and then minus A1, A2. So some complicated thing. Actually, if we choose A2, if we choose A1, right, if we choose, you know, we can basically solve this to be 0. If we do that, let's just briefly do that to see when is this matrix of T a diagonal matrix, you know. Let's choose W so that matrix of T is diagonal. Well, we need to solve A2 minus A1 equals 1, and we'll also solve, you know, A2 squared plus 2A2 minus A1, A2. Well, A1 is just A2 minus 1. Okay. Is that A1? Yeah. Okay. So that gives us A2 squared minus A2 squared. That gives us A2 equals 0, and so A1 equals -1. So A2 minus A1 is 1, and then if we check this equation, if we check here, 0, 0, 0, yeah, we get a diagonal matrix. Okay. So that's just an interesting thing that happens, I guess. Okay, so here we go. Alright. Okay, so that's the end of this video. just kind of wanted to remind you about some things about direct sums and so on. Okay, thanks for watching.